The December 1967 collapse of the Silver Bridge over the Ohio River focused national attention on bridge conditions. The resulting congressional investigation concluded that many state and local governments had inadequate programs for inspecting, maintaining, and improving bridges. Although program improvements have been made, continuing problems are a concern. The purpose of this video is to review the elements of bridge management and the importance of adequate bridge evaluation and posting. This will be accomplished in 5 sections covering bridge components and inspection standards, bridge deficiencies and deterioration, forces and material properties affecting bridge strength, the bridge posting and permitting process, and bridge management. The first section reviews federal bridge legislation and the resulting standards and introduces basic bridge types, components, and evaluations. Congress mandated the National Bridge Inspection Program in the Federal Aid Highway Act of 1968. This program established standards to specify safety inspection methods, the minimum time lapse between inspections, and inspector qualifications. Following the 1968 legislation, additional laws have been passed affecting the bridge inspection program. These laws cover requirements for the structural inventory, inspection, historic bridges, and federal funding eligibility criteria. The National Bridge Inventory now contains data for essentially all public roadway bridges in the United States. According to inventory data, there are over 575,000 bridges. Under Federal Highway Administration criteria, almost 21% of these bridges are structurally deficient and 14% are functionally obsolete. In order to ensure the integrity and safety of our bridge system, periodic inspections must be performed. An individual in charge of a bridge inspection team must be a registered professional engineer or be qualified for registration as a professional engineer under the laws of the state, or must have at least 5 years of experience and have completed a comprehensive training course based upon the Bridge Inspection Training Manual, or must have a Level 3 or 4 Bridge Safety Inspection certification. The inspector's duties include planning and preparing for bridge inspections, inspecting bridge components for deterioration, sketching bridge components, photographing specific bridge problems, taking technical measurements, making basic computations, and maintaining inspection records. Bridge inspectors currently use many inspection techniques. Close-up visual inspection is the first procedure used by inspectors. Within arm's reach, the trained eye is the most valuable inspection tool. Several physical techniques are also used. Sonic methods are used to detect hollow areas and delaminations in timber and concrete members. Hollow areas found in timber members can be further examined by coring into the wood to remove a sample for study to measure the void size. Ultrasonic techniques are used to detect cracks, delaminations, and other deficiencies in welds, steel members, and timber members. Cracks in steel members can also be detected by inducing a magnetic field with a power source. Iron compounds are applied on the member and are attracted into recognizable patterns in the area of a flaw. The dye penetrant method is used to detect cracks by applying an oil-based liquid dye, which is absorbed by the crack. After removing excess from the surface, a white liquid developer is applied, and dye extracted from the crack becomes visible. Radiographic inspection uses X-rays to locate surface and subsurface defects in steel members. Other inspection techniques and applications can also be applied as appropriate in the variety of situations, materials, and members encountered. For bridge elements in waterways and lakes, underwater inspection is needed. Often, video cameras are employed to make a record of conditions for later engineering evaluation. Adequate underwater inspection and monitoring the depth of the stream bed are necessary to identify underwater foundation deficiencies. Inspection results are tabulated on a structure inventory and appraisal sheet for later data entry and periodic submission to the Federal Highway Administration. About 116 items of data are recorded. Categories of data include identification, structure type and material, age and service, geometric data, navigation data, classification, condition, load rating and posting, appraisal, proposed improvements, and inspections. Regulations generally require bridge inspections every 2 years. However, the National Bridge Inspection Standards accommodate variable inspection frequency depending on factors such as age, traffic characteristics, maintenance programs, and known deficiencies. Bridges in poor condition or having details subject to catastrophic failure should be monitored more frequently. Several catastrophic bridge failures due to deterioration of underwater members or foundation scour have resulted in loss of life and focused attention on these problems. As a result, a 1988 revision to the National Bridge Inspection Standards established requirements for the inspection of underwater bridge members. Underwater inspection must now be performed at least every 5 years by a qualified underwater inspector. However, where the water environment is very harmful to structural members, more frequent inspections are recommended. Standards require the identification of all fracture-critical members during inspection. Fracture-critical members include tension members, such as some truss members, or other bridge components whose failure would probably result in the collapse of the bridge. Some examples of fracture-critical members are I-bars of trusses and cables of suspension bridges. Other examples are girders of two-girder bridges and the tie beams of tied arches. The 1983 collapse of the Mianus River Bridge in Connecticut is an example of a failure involving a critical member. The failure of one of 4 pin and hanger assemblies supporting a suspended two-girder span caused the collapse of the span, killing 3 people and injuring 3 others. Such failures have resulted in public demand, legislation, and regulations requiring action by responsible local, state, and federal officials to increase the safety of these critical links in the roadway system. Bridges serve 2 general functions: to span natural barriers such as ravines and waterways, and to provide man-made grade separations over other roadways or railroads. There are many bridge components. The deck directly supports and distributes the live load, primarily vehicular traffic, to other supporting members. The deck can be a concrete slab, timber planking, a steel grid or a steel plate, and is sometimes overlaid by asphalt. Rails at the side edges of the deck provide a safety barrier to retain vehicles on the bridge if control is lost. The superstructure receives the deck loads and supports the load with various combination of transverse and longitudinal beams known as stringers, floor beams, and girders. Bearings are hinge and roller or pad elements located between the top of the substructure and the bottom of the superstructure. Bearings transmit the superstructure load to the substructure and enable the superstructure ends to rotate and slide as the girders deflect, expand, and contract. Joints are also provided in the deck to allow these movements. The substructure, which supports the superstructure, also has several components. Abutments support the end of the extreme span of the superstructure and usually retain or support the approach earth fill. Caps are cross beams located on the tops of piers or piles to receive and distribute superstructure loads to the substructure. Piers support the ends of the spans in multi-span structures at intermediate locations between abutments. Piles are linear foundation elements that are driven into the earth to carry loads through weak soil layers to stronger layers. Other foundation elements include footings and drilled or excavated piers. These basic components are constructed in many different configurations and materials, such as concrete, steel, timber, and composites, to provide economical design solutions in different situations. This has yielded a wide variety of bridge types, ranging from large cable-supported and truss bridges to small culverts and pipes. However, all have one thing in common: maintenance is needed to combat the forces of deterioration. This section highlights some types of bridge deficiencies and deterioration. Bridge deficiencies and deterioration are caused by age, environmental conditions, or conditions which exceed the originally intended use of the structure. During inspection, different rating systems are used to record bridge strength and adequacy data. These include appraisal ratings evaluating safety adequacy and condition ratings evaluating material deterioration. The FHWA Recording and Coding Guide establishes numerical evaluations on a scale of 0 to 9. 9 indicates no deterioration for a condition rating or no deficiency for an appraisal rating. With time, conditions gradually decline. The structural appraisal evaluates the overall strength of a bridge in relation to the class of roadway served. The approach roadway appraisal evaluates how closely the roadway at the bridge is aligned with the general roadway the bridge serves. The deck geometry appraisal determines how adequate a bridge roadway is for current traffic demands. The vertical and horizontal clearance appraisal indicates adequacy for vehicles using a bridge or passing under a bridge. The waterway appraisal evaluates how well the waterway opening allows water to flow through it. Evaluation of channel adequacy considers the probability of stormwater overtopping the bridge for the particular watershed where the bridge is located. Scour is erosion caused by the action of running water on streambed material around and beneath bridge foundations. The scour appraisal indicates whether bridge pier foundations or abutments are or may become unstable because of scour. Bridge load and geometry deficiencies are costly for the user. Deficiencies in load capacity cause vehicle detours, resulting in added time and mileage costs. Vertical clearance deficiencies also cause detours and sometimes cause accidents. Deficiencies in deck width or approach roadway alignment may cause accidents. Since load and geometric deficiencies can be a hazard, signs should be posted well in advance to notify motorists that they are approaching a deficient bridge. Waterway deficiencies can result in constriction of water flow, causing flooding or possibly erosion of soil-supporting bridge foundations. Waterway deficiencies may also hamper navigation in larger channels. Bridge members are highly affected by the environment. However, different bridge materials show different types of deterioration problems. Deterioration of component materials can lead to structural deficiencies. Steel members corrode after significant paint or protection system deterioration. This corrosion can cause substantial loss of the net area of the metal section and thus a loss in strength. Steel members are also susceptible to cracking and brittle fracture, which in many cases is related to the effects of repeated loading or fatigue beyond an allowable level. Concrete members can show a variety of problems. Scaling is the continuing gradual loss of surface mortar and aggregate over an area. Spalling is the loss of a concrete surface thickness over an area. Such deterioration can be caused by deficient materials or construction, by unexpectedly severe environment, or by reinforcing steel corrosion. Cracking is a fracture in concrete which may be found in many patterns. These cracks may be caused by load-induced stress, restrained thermal or shrinkage volume changes, or internal chemical reactions and resulting expansion due to deficient aggregate or corrosion of reinforcing steel. When the concrete is cracked, water and external agents such as de-icing salts penetrate the member, causing corrosion of the embedded steel. Delamination is the separation of concrete along a plane parallel to its surface, often at a layer of corroded reinforcing steel. Timber bridge members are susceptible to decay, infestation, and weathering. Decay is caused by the penetration of moisture. Insects and marine borers weaken the structural strength of the wood. Condition ratings can also be affected by mechanical damage due to collisions, water erosion, and scour. Bridges may be struck by vehicles or by ships. These accidents can result in serious damage and even complete collapse of the bridges, causing loss of property and life. Underwater members are highly affected by an adverse water environment. Moving suspended soil particles, debris, and wave action may cause the underwater members to deteriorate. Scour is a critical problem when the channel and foundations are inadequate. Scour causes bridge foundations to settle, and if conditions are very severe, the bridge can collapse. Scour is the reason for more than 50% of bridge failures. Scour and other underwater problems can suddenly appear even though a bridge has been in service for many years. Deforestation, land changes, and development can gradually change the nature of a watershed, which can cause normal rainfall to accumulate in waterways more rapidly, increasing volumes and velocities to new record flows. Situations which were adequate at the time of construction can change. The Schoharie Creek Bridge failure, which occurred in New York in 1987, was due to scour. The magnitude of this tragedy is a reminder of the necessity of periodic underwater inspection and careful evaluation of foundation conditions. In order to understand the importance of strength evaluation and load posting, a knowledge of the forces and material properties affecting bridge strength is important. Sound bridge evaluation must include an analysis of the forces or loads acting upon the bridge and the effects of these loads. Forces are classified as dead, live, and secondary loads. Dead loads are forces which act continuously on the bridge, such as the combined weight of all bridge components. Live loads are forces which act intermittently. Live loads consist primarily of the weight of vehicles. Secondary loads include earth pressure, wind, temperature, stream flow, and ice. To help determine the maximum live loads a bridge can carry, engineers have produced a series of hypothetical truck configurations. These configurations simulate the many actual vehicles which use the bridge. The live loads represented by these hypothetical configurations are concentrated at wheel locations on 2 or more axles. The effects of a series of vehicles is also considered. Standard truck configurations are identified by designations such as H1544 or HS2044, which define the load magnitude, number of axles, spacing of axles, and load distribution to axles and wheels. When an engineer evaluates the strength of a bridge, a primary objective is to determine the maximum weight of a vehicle that can safely use the bridge. In this way, a bridge can be posted with an allowable load if it does not have sufficient strength to support the maximum legal truck weights. Since for short bridges, all axles of a truck may not be on the bridge simultaneously, multiple levels of total truck weight may be allowed. For example, a bridge might safely support only a 14-ton capacity for a single short truck, but a 20-ton truck-tractor semi-trailer combination might also be able to use the bridge because only part of the longer truck may be on the span at one time. The loads acting upon a bridge induce a variety of internal stresses in the bridge members. Stress is the force per unit area. Tension stress elongates the bridge member. Compression stress shortens the bridge member. Bending, shear, and torsion are other forces causing various distributions of stress and deformation in bridge members. Stresses cause strains or deformations in materials. The relationship can be shown by means of a stress-strain diagram. The diagram plots the amount of load or stress vertically with the resulting deformation or strain plotted horizontally. Some characteristics of a given material can be shown in the stress-strain diagram. The elastic region is the range in which deformation is proportional to stress. Within this region of loading, the material will return to its original shape when the load is removed. Beyond the elastic region, the yield point is the stress level above which there is a sudden significant increase in the deformation and permanent deformation if the load is removed. The ultimate strength is the amount of stress occurring at or just before rupture. To avoid damaging a structure, material stresses must be limited to a level below the yield point by a factor of safety. This stress level is the maximum allowable service stress. Different bridge members are subjected to different stresses. Cables are members which support tensile forces. I-bars and some members in trusses are also tension members. Members such as piers, piles, and some truss members primarily support compressive forces. Shear members are subjected to transverse forces or scissor-like forces. Under some circumstances, short-span beams such as pier caps are shear-critical members. Girders, beams, and stringers are primarily bending or flexural members, incurring both tension and compression, as well as shear. Connections are critical to bridge construction and strength. Because they are points of discontinuity in the materials, members with deficient connections are often the cause of failures. Connection failures can be just as catastrophic as failures in structural members. Bridges are designed for certain types of vehicles to simulate actual loadings. Overweight trucks that use a bridge repeatedly can cause a phenomenon called fatigue. Fatigue is similar to the repetitive extreme bending of a paper clip. Each time the steel is stressed, it can cause minute damage to the material until it finally breaks. If overweight trucks use a bridge repeatedly, the components may gradually accumulate internal damage until a failure occurs, perhaps under a relatively low loading. 3 factors affect the fatigue life of a bridge. First, the stress range is the algebraic difference between the maximum stress and the minimum stress calculated at the detail under consideration. Second, the number of cycles is the number of loadings that pass over the bridge during its service life. Third, the type of detail refers to specific bridge elements or connectors, such as beams, cover plates, stiffeners, welds, joints, pins, hangers, and I-bars. Some of these details are more susceptible to fatigue failure than others. For a given detail, if the stress range is large due to heavy loading, the number of cycles until failure is small. However, if the stress range is kept small by limiting the load, the number of cycles can be large or infinite. Cracks due to fatigue can result in significant loss of strength and may cause complete member failure and collapse of the structure. For the paperclip, many cycles of load can be applied if the load level is small. Similarly, bridge service life can be increased and fatigue failures avoided by controlling loads to an appropriate level. This section provides an overview of the bridge posting and permitting process. The weight limits that can be carried safely by a bridge are controlled by load posting and through weigh stations. Weigh stations are used to regulate the maximum permissible weight of trucks to the legal limits for each configuration. To ensure safety, it is critical to post bridges that cannot safely support the legal load limits or that have geometric deficiencies. Posting notifies drivers what loads can be safely carried by a particular bridge. The load limits may be a result of either structural deterioration or an original design capacity that is insufficient for today's needs. 2 types of evaluation ratings indicate the magnitude and frequency of loadings that bridges can safely support. The operating rating is the maximum permissible live load to which a bridge may be subjected. The inventory rating is a lower live load that can be safely supported by an existing bridge for an indefinite number of cycles. Posting policies vary from state to state. Some states post by the operating rating. Other states use the inventory rating. Data from the National Bridge Inventory of 1992 indicate that 20% of all bridges are load posted. However, about 4% of bridges that are not load posted should actually be load posted due to their low strength. Safety is the number one concern. The lives of passengers in any vehicle exceeding the weight limit are at risk, as well as the lives of passengers in following and oncoming vehicles. Proper sign posting warns the vehicle driver of load and geometrical limitations. Signs must be posted so that weight and height restrictions are clearly visible to the driver. Standard procedures for bridge posting vary. Most states and local governments use gross weight limit word message signs. The posting may describe different limits for different truck configurations. Before a bridge is posted, engineers must determine its safe load capacity. The safe load capacity includes a factor of safety. In this way, load posting helps prevent structural damage. Bridge posting is important, not only to prevent overstress and collapse, but also to prevent damage due to cumulative fatigue. This prevention ultimately reduces repair cost, reduces accidents, extends the life of the bridge, and saves the taxpayers money. After a bridge is posted, it is still necessary to inspect it periodically to detect any signs of additional deterioration that could affect the structural strength. Enforcement of posting is very important. Many bridge failures have occurred because excessive weight vehicles used a posted bridge. Almost 50% of the bridge collapses resulting from live loads have involved posted bridges. This alarming statistic indicates that many drivers either did not know the weights of the loads they were carrying or ignored the warnings. Some over-limit loads, however, must still be transported. For this reason, all states use permit operations to control these shipments. The primary objective of these operations is to avoid safety hazards to motorists and protect the structural integrity of the highway system. Oversized loads are loads that are over length, over height, over width, or any combination of the three. An overweight vehicle is one that is over the gross legal weight limit or over the weight allowed for a specific axle. For oversized or overweight vehicles, specific routes appropriate to the over limit are designated. Overweight vehicles are routed to bridges with extra capacity or to bridges that can carry the load by limiting other simultaneous loads or by temporarily reducing the factor of safety. The number of repetitions of increased stress range is controlled to prevent fatigue damage. There are two types of over-limit permits: single-trip permits, which are good for a single one-way or round trip as specified in the laws of each state, and multiple-trip permits, which last from 2 weeks to 1 year. Vehicles often needing special permits are trucks transporting mobile homes, construction equipment, structural members, large building or industrial equipment, agricultural and grain harvesting equipment, and forest products. Most states require warnings to motorists of the over-limit vehicles. These warnings may include signs indicating the over-limit, flags, and escort vehicles. 4 types of accessories may be required on escort vehicles: amber flashing lights, flags, warning signs, and two-way radios between the over-limit vehicle and the escort vehicle. Maintaining bridges that are properly posted and providing a controlled permitting process are critical elements in any bridge management program. Improper use of overweight permits, inadequate enforcement, and inadequate fines for overweight vehicles may result in fatigue and stress damage to bridges. This last section discusses bridge management, the process of maintaining and improving a bridge system. In order to practice sound bridge management, it is necessary to inventory and inspect bridges, evaluate deficiencies, evaluate priorities, select and program projects, and maintain and improve bridges. The eligibility of a bridge for funding through the Federal Bridge Program is in part determined by its sufficiency rating. The sufficiency rating is a numerical summary evaluation from 0 to 100, with 100 indicating no deficiencies. The rating evaluates structural adequacy and safety, serviceability and functional obsolescence, and essentiality for public use. The structural adequacy and safety are determined by the condition ratings of the bridge superstructure and substructure, or of the culvert. Serviceability and functional obsolescence are determined by the quality and condition of the underclearance, approach roadway alignment, deck condition, deck geometry, and number of lanes. Essentiality for public use is indicated by the average daily traffic, by the detour length if the bridge had to be closed, and whether the bridge is on a defense highway. Federal criteria also evaluate if a bridge is structurally deficient or functionally obsolete. A bridge is structurally deficient if it has a low load capacity, is closed, or requires immediate rehabilitation to remain open, or if key elements have poor condition or appraisal ratings. A bridge is functionally obsolete if its deck geometry, load capacity, underclearances, or approach roadway alignment no longer meet the usual criteria for the roadway served. Bridges that are either structurally deficient or functionally obsolete are eligible for consideration for matching funds under the Federal Bridge Program. Those with sufficiency ratings below 50 may qualify for replacement or rehabilitation. Those with sufficiency ratings between 50 and 80 are eligible for rehabilitation only. The funds to improve deficient bridges have numerous sources. Apportioned federal funds are distributed to the states according to relative bridge needs. Discretionary federal funds are allocated for individual bridge replacement or rehabilitation costing over $10 million, or more than twice a state's annual apportioned funds. Other federal aid highway programs include funds such as disaster relief. State and local funds might include fuel taxes, highway user taxes, general revenues, and bond issues. Federal funds allocated for bridge improvements cannot be used for earth structures, causeways, connecting roadways, interchanges, ramps, and long approach fills. Although preventive maintenance such as cleaning the drainage system, tightening loose bolts, repairing potholes, filling cracks, painting, and removing debris is critical to extend bridge life, these activities by themselves do not remove major deficiencies. Thus, preventive maintenance, although essential, does not qualify for special funding programs. Local and state governments should adopt maintenance levels of service that specify the desired condition to be maintained for each bridge component, and then budget adequate funds for this purpose. Rehabilitation or replacement options which adequately remove deficiencies are eligible for funding consideration. Bridge rehabilitation includes increasing the load carrying capacity, improving the bridge geometry and clearance, correcting mechanical deficiencies, correcting drainage problems, correcting scour problems, and performing miscellaneous repairs. When these activities are undertaken, they should be designed to assure that the improvement will be adequate to eliminate the deficiencies. Once federal funds are used for a specific bridge, it is not eligible for further federal funding for 10 years. Improvement by rehabilitation or replacement must result in a bridge which is neither structurally deficient or functionally obsolete and has a sufficiency rating above 80. If a bridge is replaced, the new bridge should be designed in accordance with standards to meet load capacity, geometry, traffic, and waterway needs for the expected life of the bridge. Unfortunately, bridge needs often exceed the total available funding. The Federal Highway Administration has estimated a national backlog of rehabilitation and replacement needs exceeding $60 billion, far beyond current budgets. To assist in assuring effective use of limited funds, the Intermodal Surface Transportation Efficiency Act of 1991, known as ICE-T, requires that states implement bridge management systems encompassing all bridges on public roads in the state. A bridge management system formalizes the activities of inventorying and inspecting bridges, identifying deficiencies and needs, evaluating priorities, selecting and programming projects, and maintaining and improving bridges. Such a system should have a suitable database, incorporate analytical tools for assessing needs, and optimize program actions among maintenance, rehabilitation, and replacement alternatives. Economic evaluation of engineered alternatives considering life cycle cost of both the agency and the user is considered to be the most defendable basis for selection of bridge improvements. The total service cost of a bridge alternative includes all agency costs, such as initial investment, maintenance costs, and rehabilitation costs. The total service cost also includes user cost, such as detour costs due to low strength or low clearance, and accident costs due to narrow width, poor alignment, or low clearance. At the same time, when evaluating existing bridges, the level of service or minimum provision for load capacity must accommodate essential vehicles. Minimum governing vehicles for local roads usually include rescue vehicles, school buses, fire trucks, electric utility trucks, fuel oil delivery trucks, residential garbage trucks, and agricultural equipment. However, on higher classification roadways, higher load capacity is necessary for many types of commercial vehicles to allow economic vitality. Similarly, geometry levels of service for the deck width and vertical clearance must provide adequate space for vehicles. Width and shoulder needs increase for higher speed and higher traffic volume roadways. The objective of any bridge management system should be to make most efficient use of available funds by minimizing the total system cost to the ultimate owner, the user taxpayer. At the same time, the management system should provide levels of service for load capacity and geometry, which will enable the nation's bridge system to meet the public's needs with safety. Proper bridge evaluation and posting are an integral and critical part of this process.